We'll proceed on different coordinate system, and we will see water tank example again, and hemisphere water tank, and we'll calculate the area. So that is the concept. Water tank, you are amazing, you are marvelous. So if I have a if I have a water if I have a water tank, okay, so water tank is a kind of a sphere, is a kind of a hemisphere. So water tank is a kind of a hemisphere. Can we try kind of the water tank that we are talking? Okay, so finally I have a sphere. Okay, finally I have a sphere. Now I'll cut it. So this is hemisphere. Okay, so this is hemisphere. This is hemisphere. Now, if I'm talking about this hemisphere, then water tank is again cut. Okay, so okay, so what water tank we are talking about now in this discussion? It is again cut from the top. this is this is water tank. Okay, so this is, if it is there, then this is hemisphere. It should look like hemisphere. It is flat though. It is hemisphere. Now I cut top portion again. This is water tank. Okay, so this is water tank where top half it is hemisphere, half is cut, and then again top it is cut. Okay, what is this surface area that is in question? What is this surface area? One thing, and then top surface area and bottom surface area. If this much still if I buy, then what is the surface area that I have to consider? So if I know it is x kg per square meter, then what is the weight that this steel would cost and how much I need to spend? Okay, so this is the this is the water tank. This is complete hemisphere, and top I took it away. I don't want full water tank, full hemisphere. Then I cover it. Now it is nice, right? This is very big. Okay, don't consider this is a fruit. This is very big, probably kind of 20-meter height. This is 20-meter high, 30-meter high, very big. And there is a stair here that someone has to climb through stair. And now he can walk on the roof. He can open it also. This is water tank. Okay. Now if this is a sphere, okay, if this is a if this is a sphere, uh, if this is a sphere, the radius of the sphere is a. That's it. So if this is a sphere, if this is a hemisphere, then radius is A. A is everywhere. And top portion, if I cut it, then radius is R. Radius is R, and bottom radius is A. Means radius of a sphere is A, small a. And if I cut it, okay, then radius is R, smaller. The height, I'm not talking about the slant height. The height from the base till this is small h. Okay, small h, r, and a. So if it is, if I take this as origin, then from here till any surface it is A. That is the radius of a sphere. I believe it is all right. Now question comes is what is the surface area that I have to ponder about? Now I have to calculate the surface area of surface area of this hemisphere. Okay, where top is again cut, height is h, and where it is cut, that radius is small r, whereas the radius of a sphere is a. Kind of can someone calculate it? So that is the question. Okay, so now we have talked about calculating the surface area. How surface area needs to be calculated. Okay, so algebra, you are amazing, you are very good. And then calculus, you are amazing and you are very good. Now consider that consider that there is a circle. If there is a circle and this is the begin point, this is the origin. This is the origin. And circle is centered at origin. This is the begin point. From here, if I go, if I go, okay, to some angle, then what is the arc length? That is the question. From here, if I go like this, then what is the arc length? In calculus, if you have velocity, if you integrate the velocity, you will get the net distance. If velocity is 3 kilometer per hour, and then if you integrate along our axis, independent axis, and then set limit for 3 hours, 3 into 3, that is 9 kilometer he has walked. So if for this curve, if I get velocity vector, if I have velocity, if I have velocity, if I have velocity, then I can calculate the curve length. If I have velocity, I can calculate curve length. If I have velocity, if I integrate, then I get the net collection, net distance. If I get velocity vector along this, and if I integrate from beginning, I can get the distance. That is the curve length. Amazing, right? So if if this is a now question arises is okay, now question arises is if this is the center, if there is a point P here, if there is any point P here, and if this is the center, then this is called position vector. So any position vector here is x. If this point is x comma y, then position vector is xi plus yj. If that is p position vector xi plus yj, then dp by dx, that is velocity vector. Okay, dp by dx is the velocity vector. Okay, so dp by dx is the velocity vector. Dp by dy I won't say, because if it is a 2D, then x and y has relationship. So if I say xi plus yj, but if I see algebraic equation, then x square plus y square equal to a square, that is the radius. Y equal to square root of a square minus x square. So I can say the position vector is xi plus yj. Instead of y, I can say fx, function over xj. Function over x is nothing but a square root of a square minus x square. So position vector is xi plus a square root of a square minus x square j. What is the velocity vector along the independent component x? dp by dx. That will come as I, xi, then I, plus square root of a square minus x square, d of square root of a square minus x square by dx, j. So this is the velocity vector. Now if I have velocity vector, I want integration. Integrations food is algebra, not vector. So if I have I plus d of square root of a square minus x square, that is velocity of dx j, then what is the, so I call it fx or y, d of y by dx, dy by dx j. What is the velocity magnitude? That is 1 square plus dy by dx whole square root. That is the velocity vector magnitude. Now, if this velocity vector magnitude, if I integrate, it will give me the curve length. So, if this is position vector, then this is velocity vector. Velocity vector is tangential to the position vector. This is velocity vector. Can you see velocity vector is also making round at each point. So, it is taking care of the curve. So, if I integrate this velocity vector magnitude, then whatever limit, upper limit I place from beginning, it will give me the curve length. If I want curve length from any 2 points, then lower limit and higher limit I have to set. Okay. Now, what is the fundamental is, that is 1 square plus dy by dx whole square root. This I have to integrate. Lower limit is by default 0 and upper limit what we want. Now, if I have a surface area, okay, so if I have a surface area, if I have a if I have a sphere, if I have a sphere, and now instead of curve length, I want surface area. If I want surface area, then I have to calculate the surface area velocity vector. Velocity vector. If I get velocity vector, I mean surface area velocity vector will be will be surface area. It won't be a line. So if this is the sphere, then this is surface area velocity vector. Okay, so it won't be a line. So surface area velocity vector, if I calculate and then if I integrate that, then I'll get the surface area. If I have a line velocity vector, if I do integration, I get the line length, curve length. If I have a surface area velocity vector, if I integrate, I'll get the surface area. Same. Now, I had fx equal to square root of a square minus x square. If I talk about surface area of a sphere, okay. Now, independent component there was x-axis. Here, independent component is xy plane, full xy plane. If independent component is xy plane, then what is dependent component? That is vertical, fxy, function over x and y. Function over xy, function over xy. So function over xy is the vertical, or that is the dependent component. So if I do differentiation of fxy along x-axis, it gives me velocity vector along x-axis. If I do differentiation of fxy or partial derivative along y-axis, it gives me along y-axis velocity vector. So if I say dfxy by dx, dfxy by dy, or fxy function over function f small f braces x comma y. If I say it is z, then dz by dx and dz by dy, that is vertical component over xy axis, would give me the velocity vector along x-axis and y-axis. If I do cross product of these two vectors, cross product gives the area. So I'll get the area where the net vector will be perpendicular to the x and y, means xy plane. So now once I get the area, I'll calculate the magnitude of the area, because area, velocity area vector, again it will be a vector. I'll calculate the magnitude and bring the bring the algebraic equation. Once I get the velocity area algebraic equation, if I integrate, I'll get the area. That is the concept. Now, what is dz by dx? What is the if I have a sphere, then any point, what is the position vector? If this sphere is centered at the origin, if the sphere is centered at the origin, from origin if I take any point P on the surface, then position vector is xi plus yj plus zk. Z is nothing but fxy. Okay, if it is a sphere, then x square plus y square plus z square equal to a square. Then z equal to square root of a square minus x square minus y square. Means any point if I take on the surface of a sphere that is centered at the origin, the position vector is xi plus yj plus square root of a square minus x square minus y square k. Now, if this is P position vector, then what is dP by dx? What is dP by dy? Partial derivative along x-axis, partial derivative along y-axis. So, dP by dx is I, j gone, I plus dz by dx k. dP by dy, dP by dy is j plus dz by dy k. Now, if I do cross product of these two, it will result in minus dz by dxi minus dz by dyj plus k. If I calculate the magnitude of this cross product, area velocity magnitude, it will come at dz by dx whole square plus dz by dy whole square plus 1 whole square root. This is the finally area equation. What is dz by dx? If z equal to square root of a square minus x square minus y square, then dz by dx is minus x by square root of a square minus x square minus y square. dz by dy is minus y divided by square root of a square minus x square minus y square. So the velocity area magnitude is nothing but x square by a square minus x square minus y square plus y square by a square minus x square minus y square plus 1 whole square. That will result into a divided by a square root of a square minus x square minus y square. A divided by square root of a square minus x square minus y square. Now this I have to integrate along the independent component. Independent component is xy plane. Okay. So I have to integrate with the d of the xy plane. dx dy. dx dy. Okay. Now the dx dy, the x, now I had taken, okay, the hemisphere, what we are talking, there is a hemisphere base plane, so base plane area we are not calculating. Then there is the curve of a sphere, then top again flat. So top we are not calculating, base we are not, we are calculating the kind of curved surface area. If this is the surface area, then whatever we have done, that is we have taken z as the value from the base. So first of all we are calculating everything for the hemisphere, because the z value or fxy we have taken from the xy plane where it is centered at the origin. So bottom hemisphere we are not talking about. So top hemisphere, and there if I don't cut it, then full hemisphere we can take care. So what is the full hemisphere surface area is a divided by square root of a square minus x square minus y square dx dy, where x is from minus a to a, y is minus a to plus a. Now x is not like that. It is not from minus a to a. Rather it is from minus a. Now if I have a hemisphere, this is the xy plane, I go height h and then cut it h. Then there is a radius r, height h, and hypotenuse or diagonal is a, that is the radius of sphere. Then r is nothing but a square minus h square square root. So if I want to calculate the curved region, if I want to calculate the curve, if I want to calculate the if I want to calculate the only the curve region, then from here till here, okay, that much I'll calculate this side. From here to here, that much I'll calculate. This is the portion what you are seeing, that is a cylinder. From here, from here, from here, from here down full there is a cylinder, and from here the right portion, left portion, all along, that we will calculate, that volume we will calculate. That is the idea. If that is the case, then the x, so if this is xy plane and there is a hemisphere, it is cut on the top, then from here to where it is cut, then flat, then where cut, and then till here. Okay, so left side and then right side. So if I take the limit of the x, then minus a to minus a square root of a square minus h square, and here a square root of a square minus h square till a. If I do this calculation, I'll get the x limit. For y limit, again minus a to minus a square root of h square minus a square, and then that side the square root of h a square minus h square till a. If I set these two limits, and the algebraic function for which we are calculating the integration is a by square root of a square minus x square minus y square dx dy, will get the round surface area. Now someone can try it. I am not saying it's not possible. So it's possible. Now if I start with the dx, then a square minus y square I can keep it as a constant. If it is a constant, consider x is equal to square root of a square minus y square cos theta. So dx is equal to square root of a square minus y square minus sine theta d theta. If that is the case, then a by square root of a square minus y, a square minus y square minus x square. So a square minus y square would come out. And then inside, what will remain there is 1 minus cos square theta, that is sine theta. A square root of a square minus y square and top square root of a square minus y square will go away. Sine theta will go minus a dx. Minus a dx will be the net integration that I have to calculate. It will come as minus a, I can keep out, then it is x. Now x from a square root of a square minus h square till a. So that will come as, okay, it is x. So it will come as a a minus square root of a square minus h square. So that is the integration. Okay, now this whatever we have got, some has to integrate through the y. So this what we have got. Now y will come again as integration as y. Y again from minus, understand, right, minus square root of, then it will be from minus a, there it was minus a to square root of a square minus h square. So I believe it will be minus a, and then square root of a square minus h square minus a to minus square root. So that I have to double it after that. This is Cartesian coordinate system. So minus square root of a square minus h square minus minus plus a. Minus is outside, then it will come as a, and then in bracket square root of a square minus h square minus a square, something like this. Same thing will come for the y also. The square root of a square minus h square minus a. Okay, so this is, I believe, it will become a square or whatever. So someone has to calculate this and get the, then double it, then get the curved surface area. What is the middle portion is the cylinder that we are not talking about at all. So that much is the surface area of the kind of uh, uh, kind of the, I'm really sweating. See the see the kind of Cartesian coordinate and this coordinate system. But anyway, now can we make it a spherical coordinate system? Can I convert it into a spherical coordinate system so that things should be easy? Now, what we started is a by square root of a square minus x square minus y square d of the xy plane. So d of the xy plane is a spherical coordinate system. This becomes r d theta dr. D of the xy plane, if I see, that is a circular region. That is nothing but r d theta dr. Now x is r cos theta and y is r sin theta. So it is a by square root of a square minus r square. Cos square theta plus sin square theta will go away. If it is a square minus r square, square root on top is a, and here r d theta dr. Now the integration what we are taking, the r will be now from square root of a square minus h square till a, and d theta is from 0 to 2 pi, much easier. So this is interoperativity. We started with Cartesian coordinate system and changed into the spherical coordinate system. The r, if I take this xy plane and there is a hemisphere, top I cut it, then r is from 0 to a. It should propagate, but it will propagate where we have cut it. The curves where it starts, that is nothing but a square minus h square square root till a. That is the r. Now I have a divided by a divided by square root of a square minus r square, r d theta dr. A I can keep outside. Now it is r divided by square root of a square minus r square dr d theta. What is integration of r divided by square root of a square minus r square? That will come as minus 1 minus minus square root of a square minus r square. I have also learned now how to do integration. Okay, so minus square root of a square minus r square. If I differentiate it, then it will become 1 by 2, and then 1 by square root of a square minus r square minus 2r. Minus minus gone, 2 gone, r divided by a square root of a square minus r square. So perfect. So minus square root of a square minus r square is the integration. Now I'll set limit from square root of a square minus h square to a. Okay. So if I do so, then minus, and outside anyway I have a. So minus I'll keep outside. So minus a is outside. Now integration is square root of a square minus r square, where r is limit from square root of a square minus h square till a. If I keep it a here, then it becomes 0. But if I keep a square minus h square, then it will become h square. So h square, the square root is h. So it is minus minus, outside minus gone. So it is a h. A, if I have kept it outside, then it is only h. Now I have d theta 2 pi, then it becomes 2 pi. So 2 pi a h, 2 pi a h. Okay, if h is a, if I have not cut it on the top and h is equal to a, then it is 2 pi a square. Perfect, right? The surface area of hemisphere is 2 pi a square. Full surface area of a sphere is 4 pi a square. Can you see? This is interoperability is so nice. Interoperability is something that really helped me. Okay. Now, if that is the case, if that is the case, then what is the surface area now? If that is the case, then what is the surface area now? The surface area, the curved area. Surface area means curved area is not for the hemisphere is nothing but for it nothing but 2 pi a into h. 2 pi a into h. Okay. Now what is remaining? I am planning to buy a steel, right? So what is top and what is bottom? So bottom is surface area is pi r square, pi r square. So pi a square. So pi 2 pi a h height plus pi a square, and top is radius r. R is nothing but a square minus h square square. So that area is pi r square. So pi and then in braces a square minus h square. So net surface area is 2 pi ah plus pi a square plus pi and in braces a square minus h square. That is the meter, that is the square meter, that is the surface area of the sheet, surface area of the steel sheet that I need to prepare the water tank. Pi 2 pi ah, where h is the height, 2 pi ah plus pi a square, bottom one and top one, plus pi in braces a square minus h square. Now if someone is buying the steel at kind of dollar alpha dollar per meter square, then he has to pay alpha into this much kilogram of the sheet is required, and then that much dollar or rupee he need to pay. Is this the end? Certainly not. So we proceeded from Cartesian coordinate system and calculated the partial derivative along x-axis, partial derivative along y-axis. That was the velocity vector. Then we did the cross product and got the velocity area vector. Then I calculated the magnitude. I got the algebraic equation of the area, velocity area. Then we got the velocity area, the velocity area, the algebraic equation. Beyond that, velocity area, algebraic equation. Beyond that, if we go, if we go, then if we go beyond that, then kind of if we integrate, then if we integrate, then we get if we integrate, then we get the surface velocity area. If I do cross product of two vectors, I get velocity. One vector is velocity vector, another vector is velocity vector. Partial derivative dp by dx, dp by dy. If I do cross product, then I get the velocity area vector. If I calculate the magnitude, I get the velocity area. Velocity area, if I do integration, I get the area. So area is this much. Now it is in function of h. H is variable. Pi 2 pi ah plus pi a square plus pi and bracket a square minus h square. H is variable. If I place h, if I place h as h as a, height is a, there is no cut word, then it is 2 pi ah, 2 pi a square plus pi a square. Pi a square is the bottom, that is always there, plus pi in bracket a square minus h square, 0. Okay, pi a square is the bottom one, and then hemisphere 2 pi a square. So it looks perfect. What we are lacking now, the place we are lacking now is that we should have started this calculation in the spherical coordinate system itself, not in the Cartesian coordinate system. Then through interoperability, we jumped into a spherical coordinate system. So we will see kind of a spherical coordinate system, again calculating the surface area of the hemisphere tank, where top is cut and then height is h. Radius of the sphere is a. What we have seen, what if we take the water tank, okay, water tank example, then first we calculated that if water tank is hemisphere, full hemisphere, and water is till level height h, or if I take cut hemisphere, then if water is full, it is height is h and water is full, then what is the volume of the water? If we see past, what we have done is, then we took the cylindrical coordinate system, spherical coordinate. Through cylindrical coordinate system, we calculated it is in a far easy way. I believe that was pi and then in bracket a square h minus h to the power 3 by 3. Pi and in braces a square h minus h to the power 3 by 3, not whole 3, h to the power 3 by 3. That is the volume of the water. But if we take a spherical coordinate system, then we calculated the volume through two ways. One is through dV, calculating the small dV and then integrating over all the area, all the volume. Another approach we took as we calculated the function fxy or fr theta. If the way we said, if I have a xy plane, if I have a xy plane, and at each xy point, if I have a fxy function over xy, that is a surface. Xy plane, if I have if I have a xy plane, and then on top at each point in xy plane, if there is a fxy function over xy plane, that is the vertical. If I touch all the vertical point, then it makes a surface. If I calculate the surface integration, it gives me the area, but there is no area, right? It is a 3D. So that gives me the volume. So what we did is that we did fxy. Here, what we are doing here is we did fxy partial derivative, we did the cross product. Then we integrated over the xy plane. Here plane fxy and integrating it over xy plane. Okay. Then two ways we calculated the volume of the water. Now when volume of the water, when we calculate fxy d, I mean fr theta and then d r theta plane, if we went through that way, then we saw that if there is a xy plane or r theta plane and there is a hemisphere, okay, then water level, when it touches the hemisphere this side or this side, that volume I can calculate keeping the limit of r from a square minus h square square root till a. Okay, if I do so, then I calculate that volume plus the cylindrical volume. That way we saw. But another way, through dV, we calculate dV and then triple integration. dV was nothing but r sine phi, phi is the vertical angle, r sine phi d theta, r d phi dr, r square sine phi d theta dr. Now, if this is a hemisphere, if this is hemisphere and it is cut on the top, and this is origin, this is the origin, if this is the origin and this is the vertical, from vertical it is phi. Okay, if this is the vertical, from vertical it is phi. Now if I see this, this is vertical here, if this is the vertical, this is vertical here, then it will make angle till it is coming till here. Can you see? Till here where the cut is there. From there to pi by 2. This is pi by 2. If this is 0 degree angle, then it makes some angle here, till here, where the kind of it is coming at this point. From here to pi by 2, I have to take the limit. Then we'll get the what volume we get with this. Okay, these are not available anywhere in the book, so we will file disclosure for it. Okay, it's not simple. Not because someone will find the volume of a water tank, because this is a new approach. So if I take phi, from phi, if I take angle, some angle, and now it is the flat cut I have from there to pi by 2. If I do so, then from there to here, this volume it calculates. Okay. If I had taken earlier, if I had taken fr theta and then fr theta and then integrating over the surface area, that is r d theta dr, then if I take r from a square root of a square minus h square till a, then we are calculating, then r is, if this is the r, if this is the r, if this is the r, then r is nothing but a square, that is the diagonal a square minus height square, that is the r. So if I go vertically down, if I go vertically down from here, then somewhere here is the r, from here to the end. If I do the integration, that slant area volume I get. What will remain is the center cylindrical region. But this is not the case here. Can you see this? There is a difference. So if I take the phi, if this is vertical, if this is phi, if I take phi from some point and then till pi by 2, from here to this slant phi, I get the volume. Okay, all around. What is remaining is the cone area in between, not the cylinder. The cone area in between, that is remaining. So this volume and cone volume, if I add, then I get the water tank volume. So this is all we have seen. Now we will see in a spherical coordinate system. Okay, so that we will see the surface area in full fledged kind of cross product and taking it will be really amazing. Means starting from the scratch with the spherical coordinate system rather than Cartesian coordinate system, and calculating the cross product and then calculating the velocity, surface area, and then magnitude and then area and the integration, amazing. So that we will see.